This is how a spirogram looks like. It consists of four volumes and four capacities. The lines you can see in orange are volumes. The lines you can see in blue are capacities. So the volumes do not overlap each other, but you can see the capacities can overlap each other. So let us look at each volume and capacity separately. This is tidal volume. Tidal volume is the volume of gas that is inhaled during each inspiratory cycle. So this is how our normal respiration looks like. This is inhalation as it goes up. This is the highest point or end inspiration. This is expiration as it comes down, and this is the lowest point or end expiration. Tidal volume is the volume during normal respiration. Next is IRV or inspiratory reserve volume. IRV is the maximum volume of gas inspired from end inspiration. As I told you, this is end inspiration. So any volume of gas you try to inspire up and beyond your normal inspiration is inspiratory reserve volume. Next is ERV or expiratory reserve volume. Expiratory reserve volume is the maximum volume of gas expired from end expiration. This is end expiration. So after having expired, if you try to expire any more gas in your lungs, that is expiratory reserve volume. And the last volume is RV or residual volume. You have forcefully expired as much amount of air as you can, but beyond that there are also some air located in dead space or in alveoli which cannot be expired from lungs. That is known as residual volume. So if you talk about the volume, tidal volume is 500 ml. Inspiratory reserve volume is somewhere around 3000 ml. Expiratory reserve volume is somewhere around 1100 ml, and residual volume is somewhere around 1200 ml. Coming to capacities, there are four capacities, each of which contains two or more primary volume. If we talk about, let me just change the color of the pen. If we talk about this one, this is inspiratory capacity. What is inspiratory capacity? Inspiratory capacity is the maximum volume of gas that can be inspired after normal expiration. You have had your normal expiration. This is the end expiratory point. As you can see, this is the end expiratory point. So any amount of gas that you can inspire after normal expiration, that is inspiratory capacity. So you can see inspiratory capacity includes two volumes, that is IRV plus tidal volume. The next is functional residual capacity or FRC. Functional residual capacity is the volume of gas that is in the lungs after normal or resting expiration. You have expired, this is end expiration, this is normal end expiration, and the volume of air that is in your lungs after normal expiration is functional residual capacity. As you can see, it includes two volumes, ERV plus RV, expiratory reserve volume plus residual volume. The next is vital capacity. This is vital capacity. Now, vital capacity is the maximum volume of gas that can be expelled from the lung after maximum inspiration. You have taken maximum inspiration. At this point is the maximum inspiration. This is up and above your normal inspiration. This is a normal inspiration point, the normal end inspiration point. This volume, as we call it IRV, is the volume that you can inspire up and above your normal inspiration. So you have taken maximum inspiration. From that point, you try to expire forcefully as much as you can until the end of your ERV. That is your vital capacity. Last but not the least is TLC. The name is self-explanatory. This is the maximum amount of gas in the lungs after maximum inspiration. You have inspired to your full capacity to the end of IRV, and at that point, what is the amount of gas that is in your lungs is total lung capacity. There are a few dynamic lung volumes to be discussed. First is forced vital capacity. Uh, and just now we discussed that vital capacity is the maximum amount of gas that can be expelled after maximum inspiration. So what is forced vital capacity? Forced vital capacity is nothing but vital capacity itself, but the amount of air that is expelled is rapidly and forcefully expired. So we can easily say that force vital capacity is rapid and forceful vital capacity. Next is time vital capacity or force expiratory volume with subscript indicating intervals in second. So I've mentioned over here FeV1. That means this is the forced expiratory volume in the first second. If I write FeV2, that will mean that this is forced expiratory volume in the second, and so on. So what does FeV represent? This is the volume of gas exhaled in a given time during performance of FVC. So FeV is calculated during performance of FVC. So this is the volume of gas while you are performing FBC and you take a time interval. So that in that time interval, the amount of gas that is expelled is called FeV in that second. So FeV1 is volume of gas expelled during FBC in the first second. So here is a graphical representation of measurement of FeV1. So let us look at it. This line A, this solid line A is the level of maximum inhalation, and you can see this dotted line B. This line represents the maximum slope of volume time curve during expiration. This is expiratory volume in your y-axis, and this is time on your x-axis. So this line, dotted line B, represents the slope of this volume time graph. Then the intersection point of these two lines, line A and line B, is considered as time equals to 0 or the initiation point for the calculation of FeV1. So your time begins from the intersection point between these two lines. So from this initiation point, 1 second is taken and a vertical line is drawn. That line is your FeV1. And after 5 seconds, another vertical line is drawn, and that line is your FVC. So this ratio of FEV1 to FVC is used to differentiate between obstructive and restrictive lung disease, and that we'll discuss in a while. And coming up next is PEFR, or peak expiratory flow rate. What does this mean? PEFR is person's maximum speed of expiration. Maximum speed of expiration. It measures airflow through large airways. Airflow through large airways. This is the point to remember. You should remember this, that PFR represents airflow through large airways, and this is classically reduced. PFR is reduced during obstructive lung disorder. The results of PEFR are classified into three zones. There are three zones I have marked over here. There is green zone, there is a yellow zone, there is a red zone. Green zone is 80 to 100% of normal. So what does this indicate? This indicates that the lung function is in good control. What does yellow zone represent? Yellow zone represents 50 to 79% of normal, and that indicates you have to take caution. And if the PFR reading is less than 50% of normal, that indicates medical emergency. Next is MEFR, or mid expiratory flow rate. So what is this? This is an average velocity during mid portion of exhalation. So you have inspired and now you are expiring. So the average velocity during mid portion is called MEFR. This is sensitive for small airway function. We saw that PFR indicates airflow through large airways, and MEFR represents that is MEFR is sensitive for small airways. So what is the normal value for PFR and MEFR? Normal value for PFR is 400 ml per minute, and for MEFR the normal value is 300 ml per minute. Next we'll discuss about flow volume loops, and get to know how these are important in lung physiology and help us to understand mechanics and pattern recognition. So a few minutes before I said that a ratio of FB1 upon FVC is important in distinguishing obstructive and restrictive disorder. So let us take a look at what happens to FB1 and FVC in these disorders. So in case of a normal individual, FB1 is normal, FVC is normal, and this ratio would of course be normal. But what happens in obstructive disorder? In obstructive disorder, there is a problem in expiration. So FEV1 is decreased. Since there's a problem in expiration, FEV1 is decreased. FVC is basically normal, and the ratio would be FEV1 upon FVC ratio would definitely decrease. So what happens in restrictive disorders? In restrictive disorder, there is no problem in expiration, but the problem is in the volume of gas that you are inspiring. There is a decrease in overall volume. Let us think it this way. In a restrictive disorder, your lungs is made up of, let's say, concrete. So you cannot expand anymore. You cannot inhale anymore. So there is an overall decrease in volume. So what will happen to FEV1? Since the expiration is normal, uh, it would be either normal, or since you are inspiring less, so there might be a decrease, normal or decrease. What happens to FVC? In FVC, overall volume is decreased. So in restrictive disorder, there would be a gargantuan amount of decrease in FVC. So what happens to FEV1 upon FVC ratio? Since the denominator is decreased and your FEV1, the numerator is normal or decreased or little amount. So this ratio would either be normal or increased. Now let us take a look at normal flow volume loop. Normal flow volume loop consists of your expiratory and inspiratory flow plotted against volume. Volume is in your x-axis and flow is plotted at the y-axis. So the normal expiratory curve is characterized by a rapid rise in expiration. There's a rapid rise in expiration. This portion, as you can see, there's a rapid rise in expiration to the peak flow rate, or PEFR. This point is your PEFR. Then there is a linear fall from PEFR there's a linear fall you can see until the loop reaches this point, and this point is your RV, or residual volume as you know it. Mm, uh, and if you talk about this portion, from this portion until RV, this portion is your FVC, or force vital capacity, and the inspiratory portion of the flow volume loop. This lower portion is your inspiratory portion. If you take a look at this one, this is quite symmetrical uh, as compared to your expiratory loop. So there can be anomaly in the expiratory loop, there can be anomaly in the inspiratory loop, and or there can be anomaly in both the loops depending upon conditions. Now we will take a look at different conditions when in which we can find anomalous loops. So here I have enumerated few conditions wherein we can find abnormal flow volume loops. Let us take a look at them separately. Abnormal expiratory loops. I'll make a point over here that abnormal expiratory loops depend upon size and location of the airway obstruction. Abnormal expiratory loops will be found in variable intrathoracic obstruction, intrathoracic tracheomalacia, bronchial obstruction. If I talk about bronchial obstruction, we should consider main stem bronchial obstruction. Then there is lower airway obstruction. We can find it in restrictive diseases. Abnormal inspiratory loops are found in variable extrathoracic obstruction. And if we talk about abnormal inspiratory and expiratory loops in the same flow volume curve, this can be found in fixed airway obstruction, extraluminal tracheal obstruction, variable obstruction at thoracic inlet, and sawtooth pattern. We will discuss about each condition separately and know how the loops differ accordingly in different conditions. The flow volume loop that we are looking at right now is a case of lower obstructive pattern. This is the most easily recognized obstructive pattern. We have a scooped out pattern of the expiratory curve. So the question is, why is there a scooping of the loop? There are two reasons behind it. Number one is compression of the major central airways with decline in flows. This is known as negative effort dependence and results in excessive airway compression. So there will be a premature airway closure. Number two reason is a disproportionate decrease in flow later in expiration. So number one reason leads to the initial fall of the expiratory loop, and number two reason will lead to the tailing of the loop until RV. So here we are looking at a variable or dynamic or non-fixed intrathoracic obstruction loop. There will be a flattening of the maximal expiratory curve due to limitation in expiratory flow. So as you can see, the dotted lines represent these dotted lines represents what the original curve could have been, but since there is difficulty in expiration, the line is flattened out over here. So the question is why there is difficulty during expiration but not during inspiration in obstructive lung disease. Let's take a look at over here. The reason is that the pleural pressure surrounding the intrathoracic trachea is negative relative to the intratracheal pressure during inspiration. So what happens is pressure in trachea is more than pressure in pleura during inspiration, so the pull is outside towards the opposite direction. So any obstruction that is present over here that causes no restraint to the inspiratory flow, no restraint to the inspiratory flow. But during expiration, the pleural pressure is positive relative to the intratracheal pressure. During expiration, pleural pressure is more than pressure in trachea. So there is a push inside. So any obstruction that is present over here, the effect is accentuated. The obstructive effect is accentuated. So during expiration, there is a difficulty during expiration in case of obstructive lung disease, but not during inspiration. Next, we are looking at mainstem bronchial obstruction. In case of unilateral bronchial obstruction, there will be a restrictive ventilatory pattern, as you can see over here. But in case of partially occluded bronchus, there will be mixed obstructive and restrictive pattern. Next, we are looking at intrathoracic tracheomalacia. This is not very important to know at UG level, but just to give a preview of what it looks like. There can be many patterns. This is biphasic pattern. This is notched pattern in case of intrathoracic tracheomalacia, and this is oscillatory pattern. It's not very important to know at this level, but just to give a preview. Next is restrictive disease. There is an overall decrease in volume. You can see restrictive disease is on the left side, is on the right side, and normal curve is on the left. There is an overall decrease in volume over here. You can see the FVC over here and the FVC over here. There's a huge difference. The pattern that you can see is called witch's hat pattern. Witch's hat pattern. The flow volume loop is tall with steep descending limb. There's a steep descending limb over here, and the flow volume loop is quite tall as compared to normal loop. Next, we'll discuss about variable extrathoracic obstruction. Variable extrathoracic obstruction is also known as dynamic or non-fixed extrathoracic obstruction. We had already seen that in variable intrathoracic obstruction, in variable intrathoracic obstruction, there is a problem in expiratory loop. But in case of variable extrathoracic obstruction, there is a problem in inspiratory loop. So there is a truncation or flattening off. There is a truncation or flattening of inspiratory loop. So what is the reason behind it? The reason is that during expansion of thorax during inspiration, the pressure in trachea is less than atmospheric pressure. So any obstruction that is present outside thorax is accentuated. Now we will discuss about abnormal inspiratory and expiratory loop. The most important condition is fixed upper airway obstruction such as tracheal stenosis. So why is there a problem in both the loops? Because the reason is tracheal stenosis can limit the modulating effect of transmural pressure on airway luminal diameter. So that results in limitation of flow during both inspiration and expiration. So there is a flattening or truncation of both the loop. Finally, we will discuss about interpretation of spirometry. We will begin with FEV1 upon FVC ratio. The normal value is more than equal to 70%. So if this ratio is normal, then we will take into consideration FVC. FVC normal value is more than 80%. So if FVC is normal, then we will do DLCO or diffusion lung capacity of carbon monoxide. If this DLCO is normal, then we have to probably think that the lung is normal. But if the DLCO is abnormal, then we have to think of perfusion disorders such as CHF, pulmonary hypertension, or anemia, etc. If we go back a bit, if the FVC is abnormal, then we have to do TLC. But if TLC is abnormal again, then we have to think in lines of restrictive disorder. We will do DLCO again. If DLCO is normal, then it could probably be interstitial lung disease. But if DLCO is abnormal in case of restrictive diseases, we have to think about chest wall disorder or neuromuscular disorder. But if TLC is normal, then we have to think in lines of obstructive disorders. If we go back a bit to the beginning, if the ratio FEV1 upon FVC ratio is abnormal, then we have to think again, look at FVC. If FVC is normal, then this is again obstructive disorder. But if FVC is abnormal, then we have to again look for TLC. If TLC is abnormal, then we have to think of mixed disorder, mixed obstructive and restrictive disorders. But if TLC is normal, then we have to again go back to obstructive disorder. So once we have deduced that the obstructive disorder is there, then we have to again do DLCO. If DLCO is normal, then we have to think in lines of asthma. But if DLCO is abnormal, we have to think of emphysema.